so far.
Okay.
What is the thing that you want to learn? Or what are the things you want to
learn? Familiarity with like leading classes and syntax for
okay.
Just how stuff works. We only briefly touched headers.
Okay.
And the separation between the CP file and the header file. So it would be cool to.
Okay. And so what about you guys?
For me, mostly like, yeah, syntax, because it's so new to me, but also like I was struggling with, so one of my professors only teaches on Windows, and then the other one only does Linux. So I was like struggling to get the file to compile.
It's a lot.
So I have at home, so I'm like, okay, I can do that, but
okay.
then I had to like, so just I guess what the difference is and why it doesn't work on.
Okay.
Like the same file doesn't compile.
Right.
So,
I like Java, right?
Yeah,
it's a lot easier.
It's easy.
Yeah. And what machine do you have?
Mac.
Okay.
And a Windows at home.
And what do you use to write code for the homework stuff?
So I'm using Visual Studio Code on this one, and then at home Visual Studio Community, because the professor uses like the libraries or something, and he says it has to be Visual Studio Community.
Okay.
So I'm using that there, and then on here I'm using VS Code with a Linux container.
Okay, how do you feel about the container part?
I don't really know what it means, but I set it up. I set it up how the professor said to do it, but like there was like a steps. So I did that, but I don't really know what it means.
Okay, sounds good. What about you?
I also want to be more familiar with using the Linux environment. I want a C line on Mac, and I've got a C line on Windows.
Okay. And do you use container with your C line?
I just set it up.
You just set it up. Okay. Yeah. Okay. That's good. Good information. What about you?
So
I mostly just brought him with me because for just because, but he doesn't know C++, but he's pretty comfortable with like coding. He's had like apprenticeships and internships and stuff. So but he's here for me, so I don't know if he has specific questions, but he doesn't know C++ either, so I was like, okay, just come in.
We're gonna have a fun day of C++, and I would say most people don't use C++ for life. If you're writing like web application, a lot of those higher level things, you don't really need C++. So that is I want to set the goal for this session, and the goal here is we're gonna start with the C++ syntax, the basics. The main focus of this session is there's a few parts that's where C++ is different from Java, from other languages. For example, if you compile here, it doesn't run on other machine. There's a reason behind it. And so all those quirky things with C++, we're going to see and try to understand a bit more. More importantly, the understand the machines through C++ is my focus here. So the reason, I don't know whether you guys thought about this. This is my view of why the school is teaching you guys or forcing you guys to use C++. It's not because you're going to use it in the future. It's really a bridge where you go from Java, where there's a lot of magic hidden behind the scene of a computer, to C++. All of a sudden, you see a whole new world through using C++. So that's the real benefit of being able to write C++. This is the school definition of 342, right? I don't know about you guys. It's hard for me to really get much information from here. But for today, at least, this is my goal, to show you a bit more about how things works on the computer, what you can see through the lens of C++. Okay. Okay, so that's really just the intro. So where do we start? We'll start from some logistics stuff. I'm gonna use C line, And because you mentioned that you are using Visual Studio Code, I'm going to try to pitch you to convince you C-Line is a better option.
I did download it for the session.
Okay, okay. So
it said it on the.
So the when we're doing the first exercise, you're gonna have some time to start it up. As long as you have C++ compiler, then the setup should be pretty easy. The biggest benefit of using C-Line is that you don't have to deal with all those container stuff. What the container is just another small machine running on your machine. Why do we need that? Because for the professor to grade, they usually grade on Linux. If you write code on your machine, you have to test your code on Linux to make sure it also passed there. I have a shirt that says it worked on my machine like that, right?
I think I've seen where that.
Yeah. So that's the situation, especially with C++, where working here on this machine doesn't guarantee it works there. So that's why the professor asks you, hey, you have to test this, and whenever you do debug or run, it should not just run on your machine, it should run on a Linux machine. But how do you have two machines running at the same time? The one option is you run a container, which is just in your system, it's gonna say, I'm gonna separate out a small area of CPU memory, all the resources, and we're gonna use this to run a small Linux there. That's all that is. So that's what a container is. It's a weird name, but that's really what a container is. And the goal really is just to, okay, we have Linux on the machine, you have Mac, we all have Mac here. So we could write code with the IDE we like, but we can run the code with the Linux compiler, which the professor uses. So that's pretty much it. And C-Line has this benefit of for most of the case, it could run code right out of the box. You don't have to do that. Yeah.
What version of C++ are you using?
Let me see. So that's my version. Yeah. But for our class, it does not really matter. As long as it's not too old. Yeah. Speaking of Linux, did you guys already have the Linux session?
Yeah.
I didn't attend.
You didn't? Okay. So I'm going to give you another way about using Linux, which is you could use the cloud computing machine. Some people, so there are a few options in terms of Linux. One, the school has all those lab machines. You could use that. You could remote into them, use that. And second is the container on your machine. The third one, you could use, for example, AWS Cloud. This is free to a certain point, but you can see that it says free tier. For us, if you just sign in with account, unfortunately you have to put in your credit card. They give you free like 500 hours for like 6 months or something. So you get plenty to use. You could also use this to get a free. So cloud is nothing but someone else's machine somewhere. So you're borrowing the machine, do whatever you want to do. Once you're done, you kill the machine, you just return it back. So you're renting the machine from someone else. And the benefit of this is you can do this now. You can do this at home. You don't have to have like a VPN to go into school. And like in the future, if you need to work, for example, for my own company, we use this to have our server there. So in the future, you can have a big machine with a lot of resources, a lot of CPU and memories. It's still good. Yeah, so that's another option. And okay, so that's that about Linux. For 342, I think it's still very important to test your code on Linux. What is the submission process for your 342? Like when you submit code, how do you make sure you pass test?
Run on a Linux machine.
Does the professor give you the test cases?
I haven't had that.
Okay.
For my projects, we don't have test cases.
So you're responsible for testing
Yeah.
that. And Do you know how the professor tests that? Does the professor have his own test cases?
I don't know, but he said that he does the grading on Windows VS Community 2022.
So he's gonna run your code.
Yes.
Okay.
I think so.
Okay, got it. And the code you submit, is that in a function or a class or?
He said that so this one wasn't like OOP, the first project, it was just like one class.
Right.
But he said in the future, all the classes need their own file and then they can zip together and then upload it.
Zip together. Okay, got it. Okay, sounds good. Yeah, there's when it comes to submitting 342 homework, there are a few things. One is it has to compile, that's the bare minimum. And second is it has to work. But since the professors are not giving you guys test cases, I would suggest you find a way to write your own test. I think we talked about that in 143.
Yeah, I learned a lot
in Java, testing is something that people feel boring. Once you get to it, it's useful. And if you write a test before you write the code, it can help you write the code. So for C++, same story. The third part, which is more important for C++, is C++ could have memory leak, which means you have to do something additional to make sure your code is correct. And we're going to talk about that in a minute. A memory leak, it just means you're borrowing money from the system. You're using, let's say, a rate. So you are borrowing the money. In some cases, you have to return it. Your code has to return it. If you don't do that, sometimes the code still runs fine. You're not going to see any error, but the memory is going to be, if you're done with using that memory and you don't return it, no one else can use that memory until the code finishes. So for the homework, it's fine, right? It runs for like half a second. For long running code, it's going to keep allocating, and someday there's no more memory left in the system, and the system is either going to kill your program or it's going to stop. And we actually, in my company, one of our servers recently had a lot of that issue. It has memory leak. All of a sudden, you got an email, hey, this file server is not running anymore. Shit. That usually happens in the middle of the night, and it's a big panic because it's not good. So three things: make sure the code compiles on Linux machine. The function, you have to test it, and don't rely on the professor to tell you how he would test it. Right? It's your code. It's your responsibility. That's true today. That's true in the future. If you go to a company, it's your responsibility. That's called somewhat ownership. You own your code. So who is responsible to say this code is correct? It's you. It's whoever is writing the code. I want to mention that as well. You guys are not doing code review yet. So if you work in a team, you write the code, but when you submit the code, it's not going to go in directly. Someone else will review your code, make sure it's correct, and then you could submit it. At that time, usually what happens is that there will be tests running. But back to the ownership thing, it's still your responsibility to make sure the code. For example, if person A, your manager, approved your code, and you push it, you merge it in, and it has some issue, causing company a certain amount of dollars, it's still your fault. So even though someone else approve your code, they are there as like a quick guard. Like you're not doing something crazy, putting like a backdoor there, but it falls on you. So that habit should start to build from today. Okay. And the third one is memory leak, and we will see that in action today. Okay. In terms of some mechanical stuff, I'm gonna use just this. Every machine is different. Unfortunately, there's Windows, Mac, Linux. They're using different compiler. The reason behind this is that C++ is compiled right into machine code, and machine code runs on a certain CPU. So CPU has its own language. So your code, when you're writing C++, is for human to read. But when you run it, it will convert that into what the CPU could understand. And every CPU, they speak a different language. So that's why if you compile it on Windows and you copy the binary on Mac, it's not going to run. because the CPU of Mac, they speak a different language, right? The unfortunate result of that is we're going to have different compiler and essentially different tool set. So here is a list of different things on different machines. Similarly, there's so many options with writing code even, right? Visual Studio is good. C-Line is what I have been using. There's a VS Code. There's Vim. Who knows Vim here? Who has used Vim? How much have you used Vim?
Yesterday.
Yes, okay. Okay. Vim is, in a way, the coolest editor that I have used. Even though today the IDE can do autocomplete, Vim is going. If you can make friend with Vim, it's going to benefit a very long run. And even in my C-Line, I have the Vim plugin, so I could use the same key combination with Vim, and you're going to see that. And if you in the future work with Linux a lot, Vim is your friend. So if you have time, spend some time with Vim. Okay, I think I wrote my entire PhD thesis on Vim because it was used LaTeX, which is sort of like you're writing code and code gets compiled into a PDF. There's no word in between there, so it feels pretty cool. And the other benefit is if I'm writing this as a code, I could collaborate with other people through Git. So it's just character, right? So it's a lot easier. And someday you might use this, yeah, so this is the language to write document. It's pretty similar to like Markdown, but it's pretty cool because now you are simply just writing characters. At the one time, we had a paper with 4 people involved. We have, throughout the whole process of writing the paper, we have never met. Like you're writing, he's pushing to Git, I saw it, I pull it, and back and forth and back and forth. It's pretty cool. So that's Vim. And of course, there's online editor, but I think today we all are able to run code, so that's fine. Any question before we go into the syntax part? Okay, so since you have, you're leaving at 2, right? Okay, so I'm gonna time that properly. But so let's start with something basics. This part is just make sure you guys can write code today. Since you already started, I won't spend too much time. First thing first, it's always programmer's heaven. Let's write this hello world. And what I wanted from you guys is just as long as you can run it, you can see the printout, then we are good to move forward. Okay. Just waiting for.
It failed.
It failed? Okay. For this part, just use whatever is comfortable.
Okay.
So for that one, is that just demonstrating that the line is from the standard library, line 3 at the end?
Yeah, yeah, the STD : part, right?
I'm seeing it as like just headline.
Oh, without this. If I run it in this way, but it'll be interesting if you put 2 of them together.
No, just as end, like without the standard library specification.
Oh, so sometimes you don't see this at the beginning. Yeah.
Oh, I know why, because it was like using namespace.
It's using namespace. Yeah, yeah. In a bigger project, you might see this at the beginning. Usually I don't suggest doing that. Is for one, you're learning, and for 2, this tells you exactly where that NL come from. If you have 2 namespaces, both of them have this. In the code, if you see one, then you have to figure out which one is it.
That's what I was thinking. I asked in class, and it sounded like you can use 2 at once, but I was thinking there might be overhead with that. Yeah,
the overhead is more like just it makes the code longer.
Yeah.
But today with the autocomplete, it's not too much of an issue. Yeah. This would be company by company. So some people, they have the standard, will always use the namespace. For like small project, it's not a big overhead. I would say just keep.
Noticing that there's big like formatting style guide based on company culture,
Oh, yeah.
not just code, but also pushing.
Yeah. And what other question do you have? I'm gonna ask you a question for you since they're working on this.
I'm ready.
You're ready? Quick, cool. One quirky thing is this is a main function and this is a return type, right? If I get rid of this, what's gonna happen? There's no return, right? And if I run it, still works. And the second question is why is returning 0? What does that 0 mean, right? The quick thing is for, especially on Linux, the return number means something. 0 means the code is completed successfully, nothing wrong. If you return like this, on Linux, you could actually see that number. It gave the indication that something did not finish correctly. So that number means something. And the other part is if you remove that, that's just a quirky thing with a compiler. And compiler will add that in when it's compiling the code. For some reason, you don't have to do that. I don't know why that's a big issue for them to implement that. Okay, since you are able to run this, quick exercise. Let's try the loop, which means we're gonna print this, let's say 5 times. It's pretty similar to Java. Let's do 5 times. And that. And I'm gonna put this here. And it should be just doing that. Good. Okay. Okay, so that's easy. Next topic is a variable. So let's say we want this to be not here. It's usually bad to have this kind of hard-coded string in there. So we're gonna take this out and put this into a string. And in C++, the string is this, just this. So I'll do this hello world message equals that. And we can put the hello world message here. Yeah.
I noticed that sometimes in the import statements, like the hashtag include.
Yeah.
Sometimes they put string.
Oh. Okay.
When would I need
that? If you see this red, it means it cannot find it. Then you have to include that. This has to do with that quirky thing that C++ on every machine is different. So it depends on where that string, what .h file that string comes from. Sometimes on my machine, it seems like it's in the IO stream. If it's not in there for some reason on Linux, let's say, then you have to include the string. Yeah. Okay, so if we run this 5 times, and the last thing for this part is let's add a number for each iteration. So first iteration should be 0, hello world, 1, hello world in the second iteration, so on and so forth. And
Space in between.
yeah, you probably want to separate them with something. So I'm gonna do this. And that's the result. It's, well, in my case, it should be starting from 0 and 5 times. Cool. So I'm gonna revert this back to 1. I'm gonna talk about the debugging real quickly here. Apparently there's a bug, and with this code, if I'm running this, it's print out 4 times instead of 5. Let's see where the lines stopped. Okay, and on C line, at least the way to debug is pretty similar to IntelliJ if you have used that before. It's just instead of clicking the green button, I think if I right click here, it has a debug option, and we want to use a breakpoint to debug this. So for example, I'm gonna add a quick breakpoint on the left side by clicking the line I want the code to pause. So here is, I'm gonna pause here. And if I do the debug, run it, you're gonna see the blue line means the highlight means the code is currently pausing there. It's pausing to give us a chance to see all the variables. At this moment, what are the values of those variables? And we have a few options here. And the simplest one is just a step over means one step. If there's a function, it won't go inside. The other option, step into, means it will follow into the function. But here, I'm gonna run one more step, and you could see the I here from inside that loop. And if we're debugging this, we'll say, hold on a second, it's supposed to start from 0 instead of 1. So that tells us, okay, that's the bug, and we can stop the debugging, and we're gonna change this back to 0. And if we run this, you're gonna see that is correct. So that's roughly how we want to debug this. It's hard to do this on a Linux machine because there's no fancy IDE there. On Linux, the tool, I believe, is called, so this is a Linux machine, and let me make this bigger. On Linux, you're gonna use this. Yeah, it's not installed, but this is like a text editor. It will still show you the code line, and you can say press N, enter. It will move on to the next one. You're like, okay, show me the variable name I. It will tell you the value. So on Linux, there's still something you can do, but it's just not as fancy as in this IDE. So that's debugging. Okay, cool. No question there. Some simple things. Let's say, I think you guys are familiar with this, the conditions, which is if statement. So let's say we are printing 5 times. I'm gonna change this to 20 times, but I only want to print the even number ones. 0, 2, 4, so on and so forth. We're gonna use the mod operation. Mod means the remainder when you do a division. And you're gonna use this a lot. So if you guys are not familiar with this, so for example, 3 divided by 2. 3 equals 1 times 2 plus 1. 2 plus 1. The remainder is that plus 1. So it's trying to divide the number as much as possible until there's no way to divide it anymore. Right? So 3 divided by 2, you can only divide by 2 once, and then what you have left is 1. And you cannot divide 1 by 2 any further. Another example, let's do 4. 4 equals 2 times 2. So you can divide 4 twice. There's no remainder because 4 equals 2 times 2. So the remainder of 4 with 2 is 0. It tells us if a number can be divided by 2. Right? Try 6. 6 equals 3 times 2. What about 5? 5 equals 2 times 2 plus 1. So the remainder is 1. If there's any remainder that's not 0, that means that number cannot be divided by 2. Then the same with if you're trying to get a remainder of 3, or not 3, 5 mod, we call this mod, 5 mod 3. So how many times can 5 be divided by 3? Once. So because 5 equals 3 plus 2. So 2 is the remainder. So 5 mod 2, 5 mod 3 is 2. Right? It tells you whether a number can be divided by that number.
For efficiency, would we do in the condition I plus equals 2 instead? Or are you going to expand on the modulo idea here.
Yeah, for this part, there are so many different ways to write it. Quickly, as you said, is if we don't do this, then we can simply do it here. Right? The original I++ is I equals I plus 1. So if I plus 2, that's good. So that's one way to write it. The other way is, as I said, this is if I do I mod 2 equals 0, we are going to print. So I'm going to put this here. So we're going to print. That's another way to write it. Just make sure it's correct. We see the even numbers. On this code, what issue do you see? Like if you ask you to improve, we have to use mod just on this piece of code. Do you see any issue? Apparently it's producing the right result. So it has less to do with the logic. Might have something to do with the code itself. So what issue do you see? Efficiency? What do you mean by efficiency?
Switch to the
plus 2, okay.
20 times when it can
run. Right. So this is running 20 times instead of, it doesn't have to run 20 times. What other issue do you see other than that? It's really small, but the issue with this, or sort of a small issue with this, is whenever we're writing C++ or Java with indent, we want to reduce the amount of indent, right? When we have this kind of code, and especially in this for loop, there's only one line. So if there's more code inside this ifs, then you're going to have a for loop, if, and the whole section, which the whole section does not have to be on the third indent here. So just on the readability, the way is we're going to do continue. And we're going to put the rest of the loop body outside, so it has only like 2 indents. So we want to reduce the amount of indents. And the continue means it's not divisible. Go to the next iteration. Give you the same result. But now the code, if we have more code here, it's much more maintainable. Instead of having a bunch of indents there, it's really hard to test. Right? Okay. But of all this, there's no right or wrong. I'm just pointing you, if you see this kind of situation, there's something you could do to improve it.
So if you know that you have an operation where you've got to do it 1,000,000 times, but there are some conditions where you don't have to do it maybe like 30, then instead of saying if it matches, then do it.
Yeah, you can reverse it. Yeah. And this is sometimes it's more useful. For example, the thing you are doing it's gonna create this, create that, do a few steps, and then you have the if statement. If it doesn't do this, then the part before the if statement, if you don't have to do that every iteration, then you might as well just put the if before it and say, if this happens, just go to the next iteration. I don't even bother creating all these things, because if I can know that it's not going to run. So that's another use of it. Okay, cool. Ifs and all right, so that's the syntax part. And the next one, I'm going to play a small game with you, and we're going to find out the result with coding. And the game is this. You have 2 options. The goal is for you to get as much money as possible. You have 2 options. One is I will give you $1 million today. Second option is for 30 days, I'm going to double the money you had from the day before. And we're going to start from 1 cent. So 1 cent, tomorrow you have 2 cents, and tomorrow after that you have 4 cents, right? And we're gonna continue down this for 30 days. the question is, do you take the money today for $1 million, or do you wait 30 days to get whatever, however much you're gonna get by then? What answer, before we write any code, what answer would you go? You want the money today, or you want it in 30 days?
I feel like whenever that's the choice, it's like either you take a lump sum or you get a compounding interest. I think it's always the one where you take, I would take the cent today or this 1 cent for the 30 days.
Right?
Yeah.
What about you?
Same thing.
Same thing?
Very common to
So guys are easy.
I think we talked about this in 143 too.
A little bit,
Yeah.
we have a similar.
The trick though is that it's the difference between like 1 million and I think it was like 10 million.
Okay.
So to quickly see that and see the difference, I had to use a calculator to see what to do to
Interestingly, I asked my wife yesterday when we were working in Home Depot, and I asked her, and she said, "For sure, I'll take $1 million." And I told her you could get more, or even $4 million more, and she said, "No freaking way, no way!" And in the middle of the Home Depot walk, we have to pull out ChatGPT and ask ChatGPT to show her the numbers, and she was surprised. So what we're gonna do today is simply just write code to convince my wife. That's the case, right? And we're gonna do it, it's print out every day for 30 days, and we want to see how much we're gonna get. Okay, I'm gonna give you a few seconds to write that. And I'm gonna write that too here. Like a 10 million something at the end, right? 5 million.
5 million. So first day is 1 cent, and that would be 5 million. Full extra day. How do you format it? Very well. When I get up to 5 million, it's just scientific notation.
Okay. For this part, I'm gonna wait until she finishes. You good? What was your ending balance there?
I also have scientific notation, so I don't know, but it's to the 7th, so what is that, 10 million?
10 million, yeah.
10 million.
Yeah. So it's a lot more than my wife thought. Then a few things here. this is a code. This code is pretty simple, but I want to show this because now it involves a floating point number, and I want to introduce another way to do print. This is from C, not C++. I came from that age, so I'm more comfortable using printf, right? So you could do ending balance, and if you do 0.2, I think that's how like just show me 2 digits. And I'm gonna divide it by 1 million. So instead of doing that, we could see that it's the ending balance is 10.74. I personally like the printf better, shorter. It give you more flexibility.
So,
Yeah.
so is the printf like similar to Java? Like you do the same?
Yeah.
Like, okay.
Yeah. It give you the formatting option here,
Okay.
and the %d and so on and so forth. Just on the code, I would say there's a few things. Okay, back to the appearance of the code. What do you think that can be improved in terms of readability? Because we just saw that it's giving the correct result.
Or could you not initialize ending balance where you
right? So
declared it? Can you not initialize it?
So yeah, you can, and that's good. Anything else?
Does this mean? I just learned about the ampersand after the type declaration, so float ampersand ending balance equals ampersand start, and that's like a constant type reference, and that whole difference. There may be issue with this.
Not really, but when we talk about the reference, we can come back to this. Yeah. Small things as for the first line, this you can argue, well, we don't really need that variable, right? It's used only once. If we do need a variable in C++, you could, if you do intend to use that only once, you can set that to constant. That's the same as final in Java, just saying, hey, that is it. You cannot change it. The other thing is whenever in your code, whenever we're dealing with something, some number with a unit. In this case, 0.01, it means actually dollar. It's 1 cent, but it's a $0.01. What you want to do is include that unit in the variable name. For one, we don't need to write the comment anymore. And whoever else is reading this, they don't have to come back to you and what do you mean by that, right? So this, I would change the name, start in dollar. So now we don't have to have this. It's actually still it's still okay to have a comment like this. When we're writing comment, the goal of the comment is not to explain the code. The goal of the comment is to indicate the intention here. The intention of 0.01 is saying, hey, I'm thinking I'm trying to define this as 1 cent, and the code is here. So if someone else is reviewing your code, they see this, and just for some reason, the code was wrong, they could see the different things. Hey, it seems like you're trying to do 1 cent, that's not 1 cent. So give other people a chance to catch the error. So it's still good to have the comment in this way, and the comments are for intention.
A question about comments. Is it typical for so one of my professors doesn't care what the comments are,
right?
But the other professor wants every method to have preconditions and postconditions,
right?
So when I do the preconditions and but he also wants of course, the comment at the very top of the code that says what the whole class is doing. So when I do the pre and post conditions for the main, I feel like I'm just restating what I put up top.
Okay.
So how do I I guess my question is like, is there too much that I can say?
Okay.
Like, I don't want to just repeat what I just said.
Right, right. That would be a good question. You also ask your professor,
Okay.
because I don't know what his intention is
Yeah.
there. But my answer is it depends. If you're doing homework and the professor is asking you to do that, it's more for you to show him what you know. In that case, whatever the professor wants, just put it there. Even though it could be duplication, it's still good.
Okay.
So that's for study, for learning. In real life, nobody cares, right? People would only care when something goes wrong on a certain line.
Okay.
And the mindset for me is I got PTSD from this. Is I don't want to read the code in the middle of the night at 3 a.m. where it says start equals 0.01. What does that mean? What unit is that? Right? Especially when it comes to money payment, you want to make it really clear. So it's still good to have duplicated information just to confirm what you're doing and other people can see that. Yeah. Cool. Okay. That's that. In this case, 1 million this, we could also put this as a const. This is going to be used here. And number of days. Okay, so that's good. I find this interesting because what can you see from the number itself? Like, it's still amazing how it goes from 1 cent to $10 million in 30 days. So what trend can you tell from the numbers? To make it easier to see, I'm gonna add also the number, the iteration number. So if with printf, that's %d, that means integer. And actually not here, but I'll add it here.
I think there was a bug in that one, like accounting logic bug, in that when you do your ending balance at the end of the output, that's going to update it past what you're seeing it happen. So when you see it happen a third time.
Okay. So let's try that. I'm gonna add
like a fence post.
I'm gonna do this.
Oh, that's good.
Right. So we want to see this double thing happen how many times? Is it 30 times or 29 times?
30. You want to see it double 29 times. So
right.
The 0th time should be the identity.
Right. And okay, so for that, I'm gonna put a breakpoint here, and we can run this real quickly. Run this. Starting there. So I is go in there. I is 0. So if you pay attention to this side, you could see the number. And if I keep going, and you could see, this is for the sake of time. I'm gonna keep going. It's not gonna take too long. It's getting interesting now. 7, 8. So this is already 30 days. And it's doing this one on the 30 days. And they come back and finish the code. Then are we counting 1 more days here? Why are we counting 1 more days here?
Because the ending balance is after the count. So day 1 is you get the 1 cent.
Right.
Day 30 is when.
So day 1, there's no double.
Yeah.
Day 1 is just one number. And that means we should not start from 0, because at this point, ending balance is already in it. So we are finished with day 1. So the bug is we should have 1 here. So the loop should go 29 times instead of 30 times. And if we do that again, and I'm gonna put out the ending balance. So it should be $5 million at the end. Yeah. We almost got another $5 million. Okay. But still, based on this number, this is very interesting. If you stare at the numbers and the number of iterations, what can you see? Like what trend or sort of interesting thing do you or can you observe there? The hardest thing for my wife to see this happening is in the first 10 iteration, you are still at $5. How are you going to get to 5 million in another 20 days? And even at 20 days, you're at $5,000 and there's only 10 days left. Like how do you even get to 5 million there? And it did, right? So it's always interesting. So I'm going to do this. And I'm going to take away the last number and plot this. And once you see the graph, it's the real amazing part. See how long this can do it. Okay, now we have it. So that's the amazing part, right? Even at here, you're like, we are not going anywhere. And I have been doing startup for the last 2 years. I feel like here, right? It's very desperate. My only hope is that is coming in the end, right? We're gonna keep working on this. We see adoption getting better and better. That's how things normally work. If you put in the effort constantly, it will compound into something amazing. So that's the lesson I want to tell you guys about learning anything, including C++, right? Today you learn about this. It feel like I just learned one more thing about C++. Keep doing it. The key thing is not if you reach that on day one. The key thing is you do small improvement over time, and one day before you know it, it's going to explode. Right? So that's a real cool thing to see here. And the next time I'm talking to an investor, I'm going to show him this. Yeah. Cool. All right, so that's that exercise. Before we move on to the next session, in C++, there's a few small things like array. For example, int data 10. This part is pretty similar to Java, so I won't spend too much time. For example, if we have an array of 10 elements, and you could do data equals, let's say, 0, and I'm going to get rid of this. Let's say 10. So this is pretty simple. Like, okay, we have this array, we're going to put some number into it. And if we run this, we get from 1 to 10. What is to learn here? To start with, so 10 numbers. If I put this to this, what do you think is going to happen? What's going to happen if you do this in Java? Out of bound, it gives you error, right? It gives you exception. But let's try it here. It kept going until something bad happened. So here is an interrupted by signal. This just means that the operating system is saying you're stepping way out of your bound. But the interesting part is before that, it allows it to keep going. So how is that? This is where we joke that the C++ gave us a lot of ways to hunt ourselves. You got to be really careful now, because in Java, there's always a nanny making sure your code does not go out of bound. There are things you shouldn't be doing. So there's always a nanny there. In C++, there's not. And this, even though this looks stupid, in real life, it could be happening without you even knowing it. You have a more complex code somewhere. You just instead of 29 times, we went 30 times, right? All of a sudden, it's not going to tell you. It will just continue running. And what's really happening here is that we are writing to memory that does not belong to us anymore. So the memory that belongs to us has 10 integers, and we're writing 10,000 to it. So once we go beyond the boundary, we'll keep writing to it. So now you are writing in someone else's backyard, into their house, into their living room, so on and so forth. At some point, that person got mad and came out and smacked you, right? So that's the situation. And it does allow you. So that's the dangerous part. So that's the thing I want to mention here. But yeah, make sure you check the boundaries. A few things about the for loop itself, which is the 3 conditions, you don't necessarily have to have them. So you could omit the one in the middle. And if I run this, what's going to happen? It will just keep going because the thing in the middle is supposed to stop the loop at some time. Now we don't have it. And as you can see, it's going to do the same thing. It's going to keep writing. And similarly, you could also not have this part. And what's going to happen here? It's going to keep going at the first element, right? My question is, if this is the case, what are the values actually after we run this loop? What are the values in this array? Because we only been written to the first one.
You only know the first. The other 9 would have whatever values they had in memory at that time.
Right. In Java, if you do this, what's gonna be the value in those arrays? 0, right? So there you could sort of already pick the difference between Java and C++. C++ give you tools that you could work directly onto the operating system. As you said, whatever was there, it came from the last guy that was using it, right? It could be numbers, could be something else, who knows? But you could see what was there. Another way to say this is because of this, you could write a virus utilizing this. You could read into what was there because we're going to talk about that in a second. Roughly, when your code is running, the code itself is in the memory. And here, the memory we have, the data 10, is also in the memory. Surrounding it are potentially our code. So you just imagine you're in a warehouse, you have your place, surrounding you are boxes that belong to other people. It could have their important things there. With C++, you could sneak into there and take whatever is there. So a quick, a very famous example is that you could change the return value, the return address of a function. So for example, if you are calling a function, when the function is done, it will return to where it was called, right? But how does it know where it was called? It keep essentially the code is in the memory. It's going to start from a certain address. Next one. Every line has a memory address there. So when you call a function, it will remember what that address is. So you go to another function, you run it, and by the time it's done, you say, I was at this address ABC, I'm going to go back there and continue from the next. With C++, if you could find where they store that address, you could change that to an address that's storing your virus code. And all of a sudden, it's running your code now. It's never going to return. Yeah.
So what if one executable is using a specific memory address and then another tries to access that same memory address while they're running in tandem, not communicating with one
Right,
another?
just by accident, right?
Yeah.
Yeah.
Is it possible to grab information or change information?
Yeah.
There's no
Yeah.
protection?
At some point, the operating system will intervene.
Okay.
But a lot of the times you could, yeah. And the situation I just described, that is very popular for a few years where, for example, I think I heard you guys talking about taking user input from your code, right? Ask user to type something. And that normally gets stored in your array, in your code as an array. And that array, interestingly, is right on top of where the return address is. So if the user, what the user type is not what you think they want to type, but they are typing in some kind of code, they could accidentally override the return address. For example, they have a return address of 123. Your legit return address is ABC. So they could just write 123, 123, 123, hoping at some time it's going to override that ABC. And once the function is done, it's going to jump to their code. And because your code is running with a good authority, their code is running with the same authority that you have. So that's called Stack Overflow attack. It's been there for a few years. So that's the kind of cool things you could do with C++ now. With Java, it's impossible. The compiler or the virtual machine will stop you there. Okay. Sometime you are just back to this. Sometimes you see this. The I++, I, that's the same in Java. So it just means when we do the plus. And if that's a bit of distance memory.
I remember, I think in Java it did the plus before the line was completely read.
Yeah, there's a easy way to remember this. So if I do this, so this is a plus I. If you see the plus at the beginning, that means it's going to do the plus first. As simple as that. So this part is going to do the plus. So it went from 1 to 2. And then it will do the print. It will use the whole thing as the result. So if you do that, it's going to give you 2. If you do it the other way, it's going to give you 1. As simple as that. Yeah. Okay. Let's take a 1-minute break.
You still have your foster cat that ran away and you found him?
We found him, yeah.
Yeah.
It was
You still have him?
yeah, no, he was adopted eventually. Let me pause. So let's get back to this. Because you're leaving early, I'm gonna switch the important things first. And I'll use this. In your current project, have you guys talked about the memory allocation?
We did in mine. So we're doing graphic images, and then at the end we deallocate the image.
Okay. What is the reason we have to deallocate it? We never have to do that in Java. So why do we have to do that in C++?
Java has garbage collection.
Right, but why can C++ have garbage collection as well?
I don't know.
Yeah.
Overhead, like unforeseen issues or surprises.
Yeah. So that is what we're gonna answer in this section. And once you see it, then hopefully the way C++ handle memory be much clearer. So basically in computer, there's memory and usually it's organized by byte. And the byte is just 8 bits. And the bit is simply 0 and 1, right? It could be 0, could be 1. And every memory location, I would treat that more like a mailbox. What do we have on the mailbox? Well, it has an address. Otherwise, how do you deliver things to there? And it could contain things. It could hold things. So that's the content. That's what you put inside that address. Also, the mailbox has a size, right? You can't put a TV in my mailbox. It's too large for it. So all those 3 things are true for any memory location. And usually it's one unit. It's called a byte, just 8-bit, 8 0 and 1s. You could put 4 of them together, it becomes 4 bytes. And we can use that to represent an integer or float. if you put 8 of them together, that's 8 bytes. And we can use that to represent a double or long. That's types in C++. So that's the bit. It's 1 byte. Yeah. And it could be something like this, right? It's pretty straightforward. In our code, every variables, they occupied some memory space. So even in this, it's a simple function A and B. We're doing the A plus B equals C. Now we're using 3 integers. And if one integer is 4 bytes, that's 12 bytes altogether. So this function is using that and it's returning something. So that usage of 12 bytes come from the whole memory. So in the computer, in this one in yours, somewhere those 12 bytes is stored there when the function is running. But in our computer, there's so much memory. It could be 16 gig or 64 gig. There's so much memory. The way the operating system organized the memory is not treating them as one big giant warehouse. Like if you want something, you go there and take it, right? It could be fine if it's a smaller, like one room with some space. If it's a giant warehouse, then if everybody's trying to take stuff in and out, it could cause trouble. So here is an example to say this. Even in this building, we have chairs, we have tables, but they're not in one flat space. You see like 2,000 chairs, right? We're spacing them out into a room. So basically there are 2 kinds. One is the shared space, and the other one is a private space. So private space is, let's say it's your desk. You have a desk somewhere. Shared space means like a meeting room, right? It can be shared by multiple people, but generally, if you want to use it, you have to reserve it. You have to say, I'm going to use this from today, from 2 to 4, so that no one else can use it. So it's very important to understand this shared and private concept. The code we saw earlier, these are from the private space. And they are private. Those 12 bytes are private to this program. And yeah, so that's just in the private section. Because it's private, it belongs to this. We don't have to reserve it. We can just use it. So here, there's no allocation, right? We just simply say, I need an integer C to store this, or I need an integer A, integer B. That's it. There's no reserve. And because there's no reserve, there's nothing to return. If you buy a book, it's your book. You don't have to return anything. But if you borrow a book from the library, you have to return it. Otherwise, you get fined, right? The same with memory. We have a 2 space, and this is private. The private memory in the system is referred to as the stack memory. Stack can also mean a data structure, but that's closely right here. There's a reason why this is called a stack. The way it's used is similar to a stack. But if you see the phrase stack memory, that just means the memory that belongs to your code, your program. When you run it, you have it already, and you can use it without having to say, hey, I need how many bytes. You can just say int something equals something. So that's the private part. The shared part is called the heap memory. Again, heap means a data structure, but here is not relevant. It's not really relevant to that data structure. It's just referring to the part of the memory in your computer that if you want to use it, you have to ask for it. And once you're done, you have to return it. The heap and the stack, okay. But why do we have 2? This is an analogy. It's more relevant today that let's say if you found a job, you want to buy a house eventually, the house, let's say, costs $1 million. How would you afford it? If you're starting today, then it takes a while for you to get that money. And let's say you're earning 100K as a first year and per year, that's going to take a while because just living in Seattle costs money too, right? You're not putting all this in there. So how do you afford a house? How do people afford a house without even having that amount of cash? They borrow, right? They do a mortgage. What that means is they go to a bank. The bank has a lot of money. They could loan it to you. So you ask for the money, you borrow it, and we buy the house with that money, with other people's money. So all happy, we move in. What happened after that? You have a mortgage to pay. And in real life, it's even worse. You have interest to pay as well, right? You pay more, but we still have to repay that. So the analogy here is the private memory, stack memory, is like the money in your pocket that you can use without telling anyone. It's my money, I earned it, I can use it. But the downside is you don't have much, right? You have like $100 in your wallet, you have a few thousands, tens of thousands in the bank. That's about it. So it's good for quick use. But that's about it. If we want to buy something big like car or house, we have to go to the pool of resources and ask for it. And usually when this happens, when we are creating a loan, it takes time. You can't just say, I want money today, and the bank will wire you the money today. It takes a process. They have to check your credit, a lot of things involved, but you will eventually get that. So stack memory here just means a small pool of memory that our code can use directly. It's fast, but it's small. The other one is slow, but large. That's the key difference. So for this part, if you remember anything from today, this is the graph I want you to burn in your mind. Just as simple as that. Okay, I'm gonna jump to the code. Oh, but I'm gonna jump to the code. So how do we borrow memory? Earlier we saw an example of 10 bytes. And we can do this, data equals this, right? We put some use to this. Where does that 10 bytes come from? Is that coming from the wallet or from the bank? From the stack or from the heap?
The specification says from the stack.
From the stack? The telltale sign is if whenever we are asking for money, we have to use a certain keyword. In C++, that keyword is new. So if you ever see this, that means we are asking for memory. And where do we assign? We're gonna assign this back to something. And assuming in your class, there's, have you guys talked about pointers?
Yeah, that's right.
Okay, so I'm gonna add that to this section. A pointer is a variable. A variable like remember a mailbox, what has three things. So if a pointer is a variable, what are the three things? It has address, which is not that different from other variable. It has a type, or it could contain a certain size things. What can they contain? What a pointer can contain is an address of another variable, which is a number. So if I ask you, what is your house address? You write it down on a piece of paper. I put that into my pocket. My pocket becomes that pointer. It's just the address of someone else's house. It's nothing more than that. So a pointer is just a simple variable that stores other people's address. Okay. And what about the size? Because you're storing other people's address, then pointer variable has to be able to store the whole thing. Normally in our machine today is 64-bit, so that's 8 bytes. And so the way to write it is to define, let's say, a pointer is just that. So usually you put a star here. Star means it's a pointer, and this part might help you. Whenever you see this, treat the whole int star part as the type. Don't think of it as it's an int, it's a star. Int star is one thing. It's a type of pointer that can store integer address. Simple as that. And if I change this to float, it's a pointer that could hold the address of a float point numbers variable. So back to this, what can you read from this line? This is saying I want to have 10 integers. So the operating system when it's running, it's going to give you the 10 integers. It doesn't give you like what does it actually give you, or what does it actually give you the code while it's running. It tells you where the start is. Once you know the start, every integer is the same size because it's sort of like an array, right? So if you want 10 integers, I tell you where the first one is. Then if you add 4 bytes, that's where the second one is. Another 4 bytes, that's the third one is. So all it has to do is to tell you where the first one is. This P or this star P, that P variable is storing the address to the first one, right? If your house is in a small neighborhood, I ask you where, you just tell me the name of that neighborhood. If I can find the first house, I can find your house. The same thing, right? All it has to do is find the first one. Okay. With that, then I'm going to change this back to data. So now we are saying, hey, instead of getting the memory from the stack, I'm going to get that from the heap from the bank. And because we are having a mortgage, sort of quote unquote mortgage with the system, data here points to the starting address of 10 integers. And once we have that, the usage is the same. You have not seen this before because in Java, we never have to use new. Right? Actually, we do have new because if we have a new class, we have a class we want to allocate an object, we would say this equals new that. So that's exactly doing the same thing here. In C++, you have two options. One, you could do exactly the same. A class name variable equals new class. You could create an object from the heap. In C++, you can also simply just do class name A. So that means that object is going to be allocated from the stack. So now you have options. And another thing that's interesting is this is a pointer, but this is as if it's an array, right? It's pretty cool. Like how are these two related? The relevance is an array. If we define int, let's say array. When we define an array like this array thing at the beginning, that is a pointer of the first element of all the 20 elements. So it's exactly the same. So for example, if here, instead of doing this, I'm going to change this array and I'll change this back to that. It's the same thing. So in C++, pointer and the array name, they are the same thing. Okay, so back to this, data is a pointer. It's pointing to the start of 10 integers. And here we are saying we're doing assign some values. With pointers, you don't necessarily have to do the bracket way. You could simply say start p plus I. Oh, okay. Data plus I. This is called pointer arithmetic. This is exactly what the computer compiler does when you do the bracket I. What it means is, okay, starting from this location, remember it's address. Starting from this location and move forward I locations. Remember, it's not I bytes, it's I integers. So if 2 integers, that's 8 bytes. And the star here means get me that storage. And I'm gonna put I plus 1, I'm gonna store that into that location.
It doesn't move I times it accesses the I memory block, or does it?
It give you the like the whole thing here. It give you the ith address, the address of the ith element. And the way you find out about that is you know its ith element, and you know the starting.
Oh, the starting is the data pointer.
Right. It's like I'm standing here, the third row. I could see that third row, and if I want to put something there, I could just put it there, throw it there. So this is essentially, I have a number. I want to store in the ith location, starting from where data is, which is the beginning of this array. Okay. Yeah.
So in Java, when we did like linked list and we had like pointers.
Yep.
You could lose your pointer. Is that something here as well?
Very good question. Yes, you can. In this part, the bad way to do this is so if you see a start pointer, if it's during the defining the variable, that just means in the start is a type. If you see it like this, when we are using it, this means find me the spot. It's called dereferencing, which just means take the address, find me that location, so I could put this inside there. And as I said, the bad way to do this is doing this. Because data used to be the first location of the array. And once you do data plus plus, now it's the second location of the array. Keep going. This is okay because you can still back off. Right? If that's really something you want to do, if you plus 10 times, you could have a loop that just send it back. So you sort of can still, in pointers, there's no going back. It's, in a single linked list, there's no going back. Right? You go from the first node to the second node, all of a sudden there's nothing pointing to the first node, it's gone. Right? In this case, it's sort of still there. Right?
So when it disappears in C++, is that a dereferencing to the compiler, or is that a dereferencing at some point, or is that just lost in memory?
In that case, it's lost memory.
Okay.
And it's considered part of one way to leak memory, because you cannot use it, but no one else from the operating system perspective, it still belongs to you. It happened to me once because I borrowed a book from the library, I lost it. Right? No one else can read it. I don't know where it is. It could be like below the seat of my car. I don't know. But I cannot use it. They cannot use it. No one can use it. So that's lost. That's a book that's lost. So in this case, if you do this, then you're potentially losing all those data. Right? So don't do that unless you have a good reason. As you can see, this part of the freedom thing that you could do a lot of things with just pointers. Back to the short-term, long-term, or small pool, larger pool. This is from the heap. And in this case, the variable I actually comes from the stack. So that's from us, so we don't have to define it. And if we just submit the code to the professor like this, that means we borrow the money, we borrow the memory, but we never return it. The return is simply this. So whenever there's a new, there has to be a corresponding delete. Not necessarily to the same variable if you change it, but you have to have a delete for the memory reallocated, right? So for example, in this case, we are allocating an array. So the data does not just one space. If we don't have this, it will return the first integer. With bracket, the intention is I'm going to return the whole thing, 10 integers. You might have a question, then when we run this, how does the system know? Right? There's no dot length. Right? How does the operating system know? Like if the code, if the CPU sees this, how does it know how many elements will return? That's a very interesting question. You could do some research about. Like how is this implemented? But it's smart enough to see that if you do this, it knows we allocated 10, it will return 10. Simple as that. So far, so good. I was saying that you don't necessarily have to return the same pointer. So for example, I could have a second pointer, XYZ, and that could just have, I could store the same address to XYZ. So those are, I have the address in two pointer storage, and I could simply just do XYZ here. It's the same thing. Okay, but if we happen to forget and we do it twice, and we run it, you're going to see that the pointer being freed was not allocated, and there's something wrong there. So that's the short term and the long term, smaller and the big pool. I'm going to get back to the slide. Yeah, so I hope next time you see code like this, it makes more sense. But that still doesn't answer the question, do we need to do this? Why can't we just put that into one big giant warehouse and we just take whatever we want to use every time? Why do we have to have a bank? Or in this case, if we have the memory of, let's say, 64 gig, why do we have to allocate it in the first place, right? That still doesn't answer that question. So the answer to that really comes down to every kind of shared resources. The benefit is someone can regulate that. So to give you an example, I think I have one at the end. So let's say there's no bank. It's one giant pool on the right. Two things are trying to use it. The color represent what they have in. So now the first one has 3, and the second one has 5. So the first program has 3 bytes. The second program has 5 bytes. So far, so good. And then the first one asks for 2 more. So get 2 more. And the second one asks 4 more, so it gets 4 more. So it's filling up. And at some point, the first one is gone. So we end up with the memory like this. Should be fine. The second one is still running. It has all the memory. But then this program says I need 4 bytes. Do we have 4 bytes there? We actually do, because there's a 4 empty space. It's just that they're not right next to each other anymore. And if we need to allocate the 4 bytes in an array for things, they have to be right next to each other. So it creates a sort of a fragmentation problem there. this could happen. Just imagine if you have all the memory and all the program on your computer trying to take, return, come in and out, allocate. Eventually, there will be many holes in the system, and it's hard for anyone to get memory anymore. So the idea is you only have a small piece. The larger piece will be managed by the system. So when it's managed by the operating system, it could give you 4 in this case. It could give you 3 from here and 1 from here, but it gives you the illusion that they are right next to each other. That's the concept of virtual memory in OS. When you go to the operating system class, you will see that. Yeah, but that itself is pretty cool. But that's why it's there, right? You can't just operate based on physical memory. Otherwise, you end up with a lot of holes.
Class I was kind of afraid of taking, but there's context to it. And
yeah, it's painful. It's
to see like why, at what level does that virtual environment?
Yeah. That's one that's gonna kick in. And yeah, when I was taking it, we wrote a small operating system being able to handle that. It's frustrating, it's painful, but once you're done, it's very fulfilling. Like you wrote your own operating system, right? Imagine that. But yeah, so this just shows the importance of having the big pool being managed by something, but you still have your small pool to be used at any time. Okay. And the downside is it's going to be slow, right? Same as if we ask the back for some loan, it's not going to happen for that. So the allocation, this part takes time. But that's just how we have to sacrifice for different purposes. And to finish up this part, I'm going to show you something real quickly. I'll give you this. Every function, if we define an array or some variables, that come from the stack. Right. So for example, if I do here int data, and this is 10 times 4 bytes equals 12 bytes. And this 12 bytes, not 12 bytes, 40 bytes. These 40 bytes come from the stack that belong to Michael. How do we figure out how much stack do we have? We just said the stack is small, but how small are we talking about? How do we figure that out? And a cool way to do this is that if the function, for example, does the same thing, int data, and we do 1 megabytes of space. So that's 1024 times 1024. And instead of int, I'm going to do char. Char means character, just 1 byte. So how many bytes is this? So 1024 is 1K, 1 kilobytes, and 1024 kilobyte is 1 megabytes. So this is 1 megabytes. And the idea here is that we're going to keep allocating this until the system crash. Then at that time, we would know how many times we have allocated this function. We know roughly the size, right? So how do we keep allocating this? So we need to keep calling full function. But the problem is that if we call it here, if we call it here, what happens? It's called once, and once we return from the full function, this is return. But we want to add up to it. We are pressure tested the stack system. So we want this function to hold it when we call it again. And the way to do it is we can use recursion here. We're calling ourselves. Because if I'm still in the first full function, you cannot release that 1 megabytes. And all we have to do is remember how many times this is called. So we're gonna add a timer here, or the times, which is times. And this is gonna say times +1. And for this part, we're gonna call full with 1. So we're gonna start from 1, 2, 3 until it crashes. Okay. And you guys familiar with the concept of recursion, right? The function calling itself. You might see that this is red. Why is this red? It's red because in C++, it's dumb. It's really dumb because it cannot see what's below it. So you have to copy paste. You either put a function above it, or you just add a declaration at the beginning. This is for the compiler to know, oh, well, the compiler is going to go from the top to the bottom. When compiler sees this, it already know, oh, there's a full function somewhere. And it takes the integer, it doesn't return anything. So for that purpose, in the top part, we don't necessarily have to provide a name. The name doesn't matter. All you need to know is it's going to take an integer as the type. Okay, cool. And so we're gonna do a print. Times. So we're gonna see how many times this print. Don't do this in production, but this is a fun experiment to see. But let's run this, see if okay, 7 times, and it crashed. So how many bytes? At least 7 megabytes. 7 or 8, yeah. If you see the nodes, yeah. So on Mac, you could do wait. What was the command that you could see? Yeah. So on Mac, you could just run this. It's called unlimited -s. So this from the system, it tells us the stack size limitation is 8 megabytes, which is sort of consistent with what we saw, right? It's called like recursively for about 7 times. And because the system, like all the program we're running, it takes some memory itself, so it's not going to be 8 exactly. But yeah, if this just shows how small that is. Remember, your code has only 8 megabytes to be used directly in a function. For anything larger, you have to call it back. You have to ask, do the new thing. There, the sky is the limitation. You can use all the memory. In fact, in today's system, if you have, let's say, 16 gig of memory, you can use more. The illusion of virtual memory is going to kick in, and if you want more space, it's going to use the disk to pretend as memory. It's going to swap things out to leave more space so your code can run, and once you're done, it's going to bring them back. So that's a whole thing behind it. Yeah, so that's the memory part. Yep.
Part of why NVMe drives are a little bit faster is because they're closer to the random access memory.
That I'm not sure. Yeah, no. But the thing is, if you're today, it's really harder to run out of memory because the system will always try to use the disk to help you. It's called the swap on Linux. I think it's probably the same on Windows as well. Yeah.
Speaking of Linux and with the time left, are there any key takeaways for setting up the C-line environment for Linux, or just use the tools that we've already learned in our classes?
How much time do you have left?
3-4 minutes.
Okay, so I'm gonna speed through this for him. This part has to do with how the code is compiled. For example, when we're running code here, so far we've been clicking the green button. What happened when we click that button? C-line is doing some magic there, right? And we do the same with Java, actually, right? We always click that button, run, but we never know. So what's happening there is C-line is calling the compiler to compile the code. The compiler convert your code into the machine code. And for different machine, for Linux, for Windows, the compiler is different. So it will work differently. But if for your homework, if it gets long enough, there could be multiple files, then how do you even compile them? You do the compiler 10 times, and how do you even do that? And with the class, some of your file would contain the main function, some don't. Then how do you combine them into one executable? The way to do that is show you this. There's a tool called a makefile. This is what you can use to compile a C++ code. So for now, if you have not done this before, just remember the name. It's called a makefile. What this does is it's going to say, hey, find all the source code that start with .cpp, and I want to convert them. So the way you do it, this is the compiler. So I want to convert this to the binary from the object, and the compiler will do this and that. Just ignore all this part. But what this file describes is how do I take, let's say, 20 source files and compile them into the binary. So that's a makefile. That's very, very, very important. Yeah. And makefile, as far as I know, it works on Linux, it works on Mac, but it doesn't really work on Windows. I could be wrong there. And the worst part is on every machine, the makefile would be different because you're going to use different compiler. So you're going to have essentially 3 makefiles for all the things, which sucks, right? So the solution to that, remember, makefile, all makefile does is you tell it, these are the CPP, this is how you compile it, but it's machine dependent. So to solve the machine dependent part, the last thing is called a CMake. It's just called a CMake. This is what a CMake configuration file look like. And what this does is, depending on your machine, it will create the right makefile for you. Right? For me, I'm on Mac. This is what the C-line used to create the makefile behind the scene. And when we click the green button, it will call the makefile, create the binary, and run it. So that's the magic behind the scene. So back to your question, the best way for Linux is if you have a project, if it has a makefile, use that. If the professor provide a makefile, that's going to tell you how I'm going to compile all this. Do not write a script to G++ this, G++ this, G++ this. Don't do that because the makefile is designed to help you compile that. So you can spend some time understanding how makefile works.
Is there any info in the CSS wiki by chance? Look it up.
Yeah, it should be there, but I can put more things in there. So just go to the GitHub, and it should have all the information there. Yeah, yeah. And remember, on top of it, the CMake just you don't have to write each makefile for every machine. You write it once, and it will figure out, oh, you're on a Mac. I'm gonna create the makefile for Mac. And once you have the makefile, you can just compile the code. Yeah, yeah. Cool. Okay. For now, let's take a quick break, 2 minutes break. Oh, since you're here, in the GitHub, the survey, the school tell me that we have to do a survey. The survey link is right here. So if you have the GitHub, just go there and leave us some. Yeah.
I was hearing Penny's also in a lab class for.
I've never heard of that. Yeah.
Which I guess is a new thing, but I'm wondering, because I don't have the time to fully commit to it as a class in my curriculum, but I do think it'd be useful to attend.
Yeah.
Do you think
Yeah.
instructors are usually willing or able for me to sit in on a lecture?
Usually, yes. Yeah.
Okay,
Yeah.
I'll definitely email them.
Yeah. And because you're here, if you have any question with C++, there's my email. Just send me an email.
Oh,
Yeah.
really?
Yeah.
Awesome.
Yeah.
Thanks so much.
I do this part-time, so
Yeah.
and I'm not teaching till fall, so I got plenty of time.
You for paying
Paying.
for Professor?
Paying, just call me Paying.
Thank
All
you
right.
again very
Yeah,
much for the
yeah,
session,
good.
Paying, and for the ice, tell your wife.
You want to take one more?
Yeah. Best of luck on cat fostering.
Yeah.
Another 50.
Yeah, thank you. Have a nice day.
Take care.
Yeah. Okay, so at this time, I'm gonna wrap up this. A few fun things to talk about is, which is 8 megabytes is quite small, right? In today's standard. This is emphasize the difference between the size of the data and size of address. If the size of data is 8-bit, the address is not directly relevant to that. The size of the data just tell you how big the mailbox can hold. The size of the address tell you how many houses can we have. Right? In this case, this is a 16-bit. So we can have 2 to the power of 16 houses or mailboxes. Every mailboxes can still hold 1 byte, or can still hold 1 byte. So there's a key difference between the two sizes. Okay, and this is talking about how small that is. Let me see. So 2 to the power of 16, we're talking about how many houses or how many byte we can have. 2 to the power of 16, that's 64 kilobytes. If every location is 1 byte, right? And now imagine if you have a computer that can only have 64 kilobytes of memory, right? What can you do with that? Not much, right? Very interestingly, the Super Mario Machine, the game was written for 64 kilobytes of memory. And there's a very cool thing what they did to, for example, something like this. They reuse a lot of elements so that they don't have to store them again. For example, the character to the left, they store 1 copy, and if you need to show the other side, then they just show it reversely. So those are using computation to compensate for the lack of memory. Same with this. If you see this, there's a lot of repetition there. Even the cloud, there's a lot of repetition. So it's pretty cool what they did back then, putting this whole thing, stuff this whole thing into 64-bit of memory. And that's to store this screen, it already takes 15 kilobytes. There's a whole YouTube video talking about how they did this. So if you're interested, it's pretty cool to see what people can do with that kind of limitation. Just to show the size, 40 kilobytes is 2 seconds of music, of MP3. It's not even in today's standard. It's just MP3, very compressed music. So in today's machine, our machine has 64-bit address. So how many bytes can we store there? The 2 to the power of 64, which is that much gigabytes. Our machine does not necessarily have that many gigabytes of memory, but that just means it could represent if you do have that kind of memory. Yeah, this is where I said when we are using, so these are memory are mostly in the heap where we have to use new, and over there really the sky is the limit, like how much memory you have, plus the operating system will fake a few more to give you. So there's a huge difference between the heap and the stack. And that's pretty much it for this part. Okay. For this part, just to see the pointers a bit more. So let's write a simple, let's do a simple exercise where we have two arrays. Let's say array 1. And we're going to do this directly. And we have array 2, which is 4. Let's do random numbers 1. Okay. The goal is we're going to call a function, find the max. And the function would print out the max value of the both array at each location. So for example, if we have two arrays like this, it's going to return 4, 6, and 3. Okay. So we're going to put the function here. And what would be the type for this? What do we pass in?
An array.
Yeah. So we need to pass in both arrays. What we are really passing in are 2 pointers, right? We're saying, hey, I'm giving you 2 arrays, and the function can do whatever it wants. But the one problem here, which is different from Java, is let's say inside this function, we could do in the star array A, the star B. So we're taking 2, why is it here? So this function is taking 2 pointers, and we need to do something, or the function needs to do something with it. Because we're finding the max value at each location, so we need to have a for loop. Right, it goes from the index 0, index 2, 1, and 2. My question here is, where do we stop here? What's the upper bound? What do we put in here?
Would it be the array length?
Yeah, the array length. And for the find the max function, how does it know the array length? I think in Java, we could do a dot length, right? But in C++, unfortunately, that luxury is gone. So we need to pass in the size. In this case, it's just an integer size. And we could pass in 3 here. And we need to remember to add this to it. Int.
So there's no way to get an array without like.
Right. Because if I give you the address of the first house, how do you figure out how many more houses is there? There's no way, right? It could be a limited amount. So we always, in this case, we have to pass in the size, and we could pass the size here. And we're gonna say too smart for this, but because we are caring about the larger one, we can simply do this and print out the larger one. And if we run this, print out the first one. Why is it only print out yeah, it's only printing the larger one. So we need to have else. Yeah. So far, so good?
Yes.
Yeah, okay. So let's say we change this. Instead of printing, I want to create a new array. And return that new array containing the largest element at each location back to the main function. So we're not printing anymore, but we need to, at the end, we need to return something. What do we return? How do we return an array? The concept is the same, right? If I return the address of the first element, then the caller, whoever received that address, should be able to find the rest. So what we return here is nothing but a pointer. And again, when you see this, just read this as one thing in the star. And we can change this to in the star. And this is where it gets interesting. Where is that array we return? We cannot use A and B. We're not supposed to change that. So we need a third array. But can we do int return array? We call that the result size. And return the result. Can we do this? Well, we can try it, right? So in this case, I'm going to say result. We can use that ternary. This is to say if this is larger than that, we'll take the first one. Otherwise, we'll take the second one. So by the end of this, we could put a breakpoint here. And if we debug this, we see the result, and we see that's the correct result actually. 4, 6, 3. Okay. And we return the address of that one, and let's say the int star max result equals this. And then in the main function, once we get the returned address, we can use that to find rest of the data. Okay, run it. That doesn't look right, right? So do we have some bug here? I'm gonna do the debug as well. So if we debug, we are stopping in the here in the find max function, and we could see 4, 6, and 3. And if I keep going back here, so that's exactly the same thing returned, and we are printing them out. And it sort of crashed at that point. What is the issue here? It was right here, but it was wrong once the caller received it. The reason comes from the difference between heap and stack. This is on heap, but this is on stack, right? A stack is, remember, that's for temporary use. So temporary means if this is defined inside this function, it's only valid inside this function. What happens in Vegas stays in Vegas, right? Sort of situation. So once the function is done, this is returned or destroyed by operating system. We never really allocate this with new. We never really ask anyone for it. So we don't have to return it. And the operating system, once the function returns got here, it will take care of this. It will take care of this. So if we return this, we are returning at the address pointing to a piece of memory that used to make sense, but does not anymore after the return. So we're returning an invalid address, invalid in terms of it doesn't belong to us anymore, and we're still holding on to it. It's like I sold my house, and I kept the key. Once we get the result back, we are using that old address to access it. It's like I sold the house, I have the key. Even though the new owner has moved in, someone else is using the house, I still go back there trying to get my stuff, right? So that's wrong, and that should not happen. That is why we are seeing all this, because we're accessing invalid memory. Okay, how do we solve this? Well, the root cause is really this is on the stack, and stack would go away when we go out of scope. The scope here is this function. So when we go out of this function, the stack is gone. But the heap will still be with us until we return it. Right? It's our memory. I borrowed this, and I'm supposed to return it. But the upside is I get to choose why I return it. So in this case, we should, instead of using the stack, we should use the heap. And the way to use the heap is to say the result equals new int size. This instead is allocating memory from heap. Okay, and if we run this, now it's correct, right? Because it stays with us. Once we allocate it, we can pass this address into any function. They can use it, come back. And we don't have to worry about, oh, it's going out, it's taken away from us. It's never going to be taken away from us until we return it. That being said, we should remember to return it. So the return it is delete bracket max result. Any question?
This makes sense to me.
Okay.
I have a question. So in my 342 lab, we learned about reference using ampersand.
Okay. So that's the most confusing part for me as well. So now that you mentioned that, let's talk about that real quickly. Reference. And I hate the reference. Took me years to come to peace with the fact that now C++ has reference. Because when I started, it was C, and early version of C++, there's no reference, right? So what is reference in C++? What do you think a reference is?
But is it not like it's, I feel like, see, that's where I get confused on the difference between a pointer and reference.
Yeah,
Because isn't
yeah.
the reference just pointing to the address?
Yeah.
Where it's stored?
Yes.
Okay.
Yeah. And the unfortunate follow-up question, if they are the same thing, why do we have two different concepts for the same thing, right? What is a reference? With analogy, a pointer is place where we could store the address of another thing, another variable, or another memory location. Reference is a name tag. What does that mean? So if we define a variable, let's say ABC equals to 5. Just using that same mailbox analogy, ABC has an address. It does store 5. 5 is inside that mailbox, and it can only hold 4 bytes. It's called, this mailbox is called ABC. Just take a sticky note, put ABC, the string ABC on it, and stick that on the mailbox. Let's say tomorrow you want to say, I don't like the name ABC. I want to have a different name. And you could take another sticky note and put the DEF on it and stick that new sticky note onto the same mailbox. That is a reference, which means if I'm talking about ABC or I'm talking about DEF, they mean the same thing. So for example, int reference, DEF equals ABC. I don't know why it put it here. DEF and ABC here, they are two names for the same variable. Same memory location, same size, same type. Now it has two names. How do you know it? How do you prove they are the same thing? For any variable, the unique identifier is their address. If they are the same address, they are the same thing, right? So if we print out x, so %x just means %x is usually used for printing out address. So I'm going to print two things. One is, let's get the address of ABC, the variable. And let's also get the address. Don't look at this yet. Let's get the address of DEF. And the way to get the address of a variable is by using the ampersand in front of it. This and this are two different things. This similar to a type. So int star is a type here. Here we're also defining a variable. So int ampersand, that's a type. So that means it's a reference referring to a integer. So when you read this, when it's defining variables, treat this as one thing, one unit, similar to int star. But here, the ampersand means we are getting the address of this DEF. And if we run this, I'll put this here. This means a new line. Let's see, where's that 4? Oh, 4 is the next part. So I'm gonna put a ampersand. But you can already see that they are the same address, right? They're the same box. Now we have two names on it, and you can put any name on it. So that is really what the reference is. In Java, that's not what that means. In Java, if you create an object, that's called a reference. You pass by value of a reference. In Java, reference means pointer. That's the bad part of the confusing. But in C++, when you see, in this case, whenever you see DEF, for example, we do DEF++, that's just ABC. What's crazy is this. You're just assigning yourself to yourself, right? But as I said, the important things here is they have the same address. That's all that matters. If they have, I don't care what the name is. If they have the same address, they are the same box. Right? Then the question after that is, seems like it's still doing the pointer thing, right? Yes, we can have different names to a variable, but do we really need this? Like, the way I could answer that, or the way I could make peace with that is, I'm gonna give you an example. So let's say we write a function called the max plus 1. We're gonna take A and we're gonna take B. And just for now, I will get rid of this. Okay. What this does is it will take two numbers. It will increase the larger number by 1. In fact, I'm gonna make it easy. I'll just call this just plus 1. What this does is it will take a number, it will take a variable, and it will increment that number by 1. But what we increment is not inside here. I want the number passed in the main function to be incremented, right? So for example, if we do return a plus 1, and in this case, we are not allowed to return anything, so it's going to be void. And let's say we call this plus 1. And yeah, so we have ABC in the main function. I want to increment ABC by 1 to be 6 by calling this function. If I do A equals A plus 1, would that work?
It's out of the scope. Like it won't remember it in the main.
Right. And the reason is when we call this function, the value of ABC is going to be copied into this local variable. Remember, this is also on the stack of this program. But we have this variable on the stack. We copy the value to it, and we do the calculation. But everything happened here is on this. It has nothing to do with ABC anymore. Two different boxes. So even though it could, if you print the A here, it's going to be 6, but this remain unchanged. So how do we change this instead? That means if you want to, let's say I have a cat in my house. If I want you to go there and feed the cat, I need to give you the key, right? I need to tell you where the house is. That's the only way you could do that. So the way here, we need to change this to take the address of the function, or take the address. And the way to do that is instead of int star, instead of int, we have to pass in the address. And when we do that, we take the address, we put that in. And remember, if this is a pointer now, this is not what we are trying to do, because this is doing math on the address itself. And what we want is, okay, take what's in address A, take the value of A, which is the address, take the value by putting a star in front of it, and the plus 1, and store it back to the same location. So the star means just go to the address which is stored in A, take its content plus 1, and put it back to the star A on the left. And once that happens, and we can see that now it becomes 6. Okay. So this is how we could achieve this by using pointers. If this is the case, where does the reference thing come in? How do we do this with a reference? Can we pass in a reference?
We did in my lab.
Right,
So I think
right.
so.
So how does that work? So if we pass in a reference, the concept is we are using let's see, put a reference here. The key line is this now. Because we are passing in a reference. This is from the IDE, so this is not part of the code. We are not saying pass in the value of ABC. We're saying I want to pass in the variable itself, which include that space storage. And so when it goes to the function, what the function receives is actually the same variable, same space, same box. And because of that, if we do this, it's correct. Because at the end of the day, we are still operating the same box ABC. So if that's the case, why do we do this? Because we can already do that with a pointer. Why do we need this? What's the point? The way I could make peace of this is it's a syntax trigger. What that means is, if you look at this part, there's no ugly star in front of everything. It looks better. It looks cleaner. And here, we don't have to do the %, at the beginning anymore. It's just as if you are passing in this variable itself. So behind the scene, if you see the compiled code, it's the same as the pointer. There's no difference there. Yeah. So that's the only or there may be other purpose. I'm curious what the professor says there, but for me, that's all that matters. Just make the code easier to read. And if you're operating, for example, if the function is really, really long and does a lot of things, it's nice to not have to put a star everywhere. And if for one place you forgot to put a star, it's a hard bug to debug because it will not stop you, right? Now you're saying, oh, take the address value, which is a long number, and crunch that into something else, which is not what you intend to. So that could cause a lot of trouble down the road. But this avoid all that. So inside this function, it's very clean, right? For me, the bad thing is if you're just reading this, if you didn't pay attention to this part, then just from here, it's not specific telling you what this is doing, right? Is this doing just here, or this is changing the ABC up there? So I personally prefer clarity. I want to see this code. I know exactly what it does, instead of having this luxury. It's like, for me, driving a manual car is more control. I know what exactly is going on. I can control it. Instead of driving a car that does everything for me, and if the road gets slippery, I don't know what it's doing, right? So this is, whether you use this or use star, that's a personal choice, right? So this is pretty much about the reference in C++. Any question? Cool. Got it. Okay, good, good. All right. So that's that. Let's see. Just going back to where we were before, right? Remember, if we need to allocate, or in this case, if the +1 or if the function there need to return another array, allocate that using new, right? See if I can Control Z back there. Right. So this is it. Still work. Okay, so I'm getting back here a bit, and there's something I want to show you real quickly. Right, this is the same function. We take two array, we call the function create a new array, does the magic, and return the new array. It's returning the address of the new array so that we can access here. We delete that here. Currently, this code is running on my laptop. So I'm gonna copy this And I'm gonna move to a Linux machine and show to you how you could find memory leak, right? The worst way to find a memory leak is by staring at it. Like if you have 20 files, it's impossible to find where that is. Okay, so this is a Linux machine, and I'll do test test button. Okay, so I'm gonna do a simple find max.cpp. Copy the same code here. And just to pretend we have the memory leak, I'm gonna comment this out. And let's compile this. Done. And we have this around. We have this executable. It's a bad name, so I'm gonna -o find max.x. On Linux and Mac, we don't need to .exe. The extension name does not matter. The way to see what the file is, the command is you use a file and you get a file name. So this file tells you, hey, this find.cpp is a C source, it's a text file. If you do the same with find x, it tells you it's an executable. So that's how at least on Linux, it tells what file is that. Okay, so we run it, same result. Seems all good. So how do we know whether we have memory leak here? To test memory leak, we use a program called the Valgrind, which I don't think this has, but I'm going to install this. This Valgrind thing is a program people use to find out whether there's any memory leak. And to use it, it's pretty simple. To use it is the way you run the code. For example, in this case, what's the name again? The way we run the code, simply put a Valgrind before it, and you run. At the end, I give you a summary, and this is telling you there's 12 bytes lost. Why 12 bytes here? So if we show the CPP, why 12 bytes? It's 3 integers, right? So that 12, sometimes it's useful to tell you roughly where the memory leak is. Ideally, this should be 0. So the way to solve this is we remove that comment and remember to compile the code again. And then we run the code and voila. This is what you need to do for every code you submit to the professor. For normal writing, it's fine. In my 342, you remember the GitHub thing that for 143 homework submission? For my 342, that's built into that already. So when you submit that, there's one more step that the student could scream at, which is there's memory leak. So they don't have to do it, but if the professor does not have that, you have to do this yourself. This is why having access to a Linux machine, for example, the container thing, that's going to be useful, right? Okay. So that's how you find out whether there's any memory. It's not necessarily memory leak. If there's any memory issue, it will tell you. For example, let's say instead of 3, we're going to do 30, which at the beginning we know is bad, right? But we also know that if we just simply run the code, it might not stop you. But let's try running this through Valgrind. Here it says no memory leak, which is true. But if you go up there, it's giving you more information and use of this. So just seeing all these things, it gives you some clue what happened there. And somewhere it might also tell you what line it is happening. But yeah, you can use VeriGrind for this purpose. It should be very clean. Once you run this through VeriGrind, there should not be any output. And that means it's good in terms of memory. On Mac, I have not found a way to do that. The only way I know how to do that is on Linux. It has to do with how the kernel works. It's just not as easy way for a developer of VeriGrind to put that on Mac. But if you ever find it, let me know. Yeah. Okay, cool. Let's take another 5 minutes break.
But I mean, it's nice to know. Okay.
Oh, speaking of that, in the math class, do they still use MATLAB? Do you know what MATLAB
He
is?
brought it up.
Okay.
He did bring it up, but I don't know if we're gonna use it, but he did bring up MATLAB.
Then what do you use to compute like a matrix multiply?
So far we're just doing it like on paper.
Okay,
not doing-
okay.
yeah.
If you do any computation, because MATLAB used to be the thing for people to learn matrix multiply or learn all the linear algebra stuff. I wonder whether they're still using it.
Yeah, he did bring it up and asked, if anyone had used it before, and then, but I don't think he said. I don't know if he
Is
said-
there any? Was there anyone raising hand?
Yeah, a couple people.
Okay. Okay.
I don't know what they used it for, but yeah, a couple people said that they did. And then. Yeah, and then we didn't really talk about it again.
Okay. And have you heard of MATLAB before?
Not before that class I had.
Just when we were in the break, the connection from me to MATLAB is my professor. I show you the software, right? The LAPAC. MATLAB is underneath MATLAB is using the library, and the founders, one of the founder, I think it's probably the only founder of MATLAB, is the professor of my professor.
Oh.
So there's a connection there, and the company name is called MathWorks. It's in Boston. I did an internship a long time ago there, spent the whole summer in Boston. It's pretty nice. So if you ever look for any internship between computer and linear algebra, that could be an option. It's a very cool company. Back then, they have free dinner. If you stay after like 8, then it's free. And we had a rotation who will call the restaurant to get the food, and that person has to call everyone on the list to come down. Sometimes the CEO is there.
Oh.
So you can see it that way. So it's a private company. So they are, the reason I was asking about that is I wonder whether they're still doing okay. I haven't heard too much, but yeah, that is a good place to work at, actually. And at Boston, you get access to all the big museums and like all the goodies on the east side.
Yes.
Yeah.
I went there once before in 2016. My mom lived there for a time, so she immigrated there from Korea. So she loves Boston. That's like her
Right.
second home, I guess.
Mm.
Yeah, but we went in 2016. It was really cool.
Yeah. A lot of the town is called a Natick, where that is, and it's where there's a lot of people from Brazil.
Oh, interesting.
You could tell because if you go to any gym, you see people playing soccer and they're really good.
Oh, yeah.
Yeah, yeah. I think the name is Steve or Steve. We call him Steve. It's not Steve something who founded us. Cleve? Maybe Cleve more. Oh yeah. Not Steve. This person. Yeah. Okay, cool. We only have a few small things left, so I'm gonna do it the one session, and that's pretty much it. Any questions so far? Okay, good. So the last part really has to do with the compilation, and we mentioned a little bit about the makefile. So I'm gonna show you here on this machine. I'll get the GitHub repo and clone it here. Okay, works. And inside this repo, we have, see, so we have the code here, right? So how do we compile this? The compilation process goes from the source file to the machine assembly. For Java, it goes from the source code to this intermediate format file. That can be recognized by all the operating system. So on Mac, Windows, Linux, Java has a Java virtual machine there to interpret what that intermediate thing is. That's why you could copy that to any machine without compiling, and it will still run. For C++, then we are compiling directly into the machine code. So that's why, as I said, it will only speak the language of this CPU we're on. And the way to do that is by using a compiler. On Linux, that's a G++. So if I do that, it will produce this executable. And if we do that, it will run. Have you guys mentioned that if you have multiple source code, how do you deal with that? Okay, so let's see, we have a man, and I'm gonna put a second file there, which is full.cpp. And in this file, we'll just say full, it doesn't really do much. Let's put a number there. Int a, and we're gonna return a time a. What was I thinking? And we're gonna return a time a. And so that's the full function. And so here, we're going to say int x equals full, let's say 12. So put them together. The top is the full, is just a function. And the bottom here is the main function. So this is calling that one. And now the question is, how do we compile this? So if we do the same deal using G++ man, it will tell you that it doesn't know where the full is, right? So we need to include the full here. And the simplest way is just putting that there. and it still says it's not found. And it says the full is not declared because from inside the main function. That just means the main function is compiled the function one by one. So when it gets to the main function, it's like, I don't know what this full is. The compiler does not know what that is. What if we change the sequence? What if we compile that first? It still doesn't know. So how does it not know? The problem with that is when it's compiling this, it sees the full, it doesn't know where to look for. So the idea is, or the solution is where the include come in. You might find it weird. Why are we including a CPP file, right? Usually it's a header file. But first, let's see whether this works. It worked. And if we call it out, it does, where's the print? Oh, print. So compile again, run it again, we see the 144. A few things to notice here. We included the foo.cpp, but the one we are compiling, there's no foo.cpp anymore, right? Why do we not have to put the foo.cpp here? What we could try is if we put the foo.cpp, if I do this, what's going to happen? Says multiple definition of foo. How is this multiple? Because in the main file, we included this and we are providing this. That's the same file. How do we have multiple definition? It's very interesting, right? And the way this works is the include, what this does is it's going to read the entire content of foo.cpp and put it right into this file and then compile this as if it's one file. So by the time the compiler sees this, there's no include foo.cpp anymore. It's just whatever is in full, it's going to put them all together. Okay, now you have the main file which contains the foo.cpp or the content of the foo.cpp. And we have a second file which also contains the foo.cpp. So at this time, when we run this, G++ will see two versions of it. One come from the main, the other come from the foo.cpp directly. And it's like, why am I seeing two? Like, which one am I supposed to call? That's why you see this multiple definition thing. This also tells you that the include at the top, it doesn't matter. It's a header file, it's a file, right? It does not have to be a header file. It's a file that whatever code you want to be included into this file, you could include that. That's all it does. Okay. Then this I have to say, this is not the standard way of how C++ should do. The standard way is to say, I'm going to open this. We have foo.h, sometimes it's called HPP. In here, we are going to only have the declaration. So at the top on the left, we have the declaration. This is the actual function body. And inside the, so I'm going to close this. So inside here, we should include the header. This is not that different from just saying int full int, having it here. But instead, it's coming from a separate. But the point is, in that file, you could have more and more stuff. In fact, if we are already including that, the HPP in the main file, we could also put this thing here. Because now the foo.hpp become all the headers. Everything we need to include so that in the main function on the right is pretty clean. We just include one thing, and that's it. Okay. So now we have 3 files. How do we compile this? We can do G++, main, full CPP, works. Why does this work? Because inside the main, we have the include. And that actually shows you what when this compiler compile this code, what does it need to see? It doesn't need to see the body of the foo. It just need to see a declaration. Someone tell me there is a foo function somewhere. As long as G++ sees that in the main function, it's happy. It's going to continue down to the rest. In this case, it does see that from the include. And that's also the reason we're not putting the include here, because it's already included into this. So when we have this view, it's happy with compiling this, it's happy with compiling this, it will eventually put them together into the file. The actual process actually it goes like this. It will first compile the main. Let's call it the main.o. The .o means object. So this .o is partially compiled code. Remember, for the main function to function, you have to have foo, you have to have main. So if I just do this, it will only compile the main and into like half-baked thing as the object file. And it will do the same. So now we have 2 object file. And the last step we could do is, okay, just put those 2 object file together and produce the foo.x. And now we have the foo.x. And the .o is, we don't have to look into it. The .o, if you do file foo.o, it tells you it's a binary file. Relocatable sort of means this is part of the program. So you could put that into another thing to combine that with another part of the program to form the final program. So there's a pieces of the executable. It's not executable. Just for this part, any question? And this is the same process whether you have 2 files, 200 files, same process. You're going to compile them into .o. When we did this, it's just saying, hey, don't bother producing 2, just do it as part of the process. Behind the scene, it's still doing the 2.0 and combine, right? So how is this related to makefile, right? So for that, I'm going to cheat here a bit, and I'll copy the whole thing into ChatGPT and ask that to write the makefile for us. Convert this into a makefile for want. Yeah. So this is the content of the makefile. I'm going to copy this and come back here and put that into a file called the makefile. This is essentially what we just did, right? And the way to read this is there's a colon. On the left, we call this a target. And this is to say, to create this, we need this 2 file. And once we have this 2 file, we would run this to create this. But how to get this, then same deal. To get this, we need this file. And once we have this file, we're going to run this to create the .o, the same here. So it's sort of like a recursion. So very similar to a tree structure. Like you go there, there's more, then more and more. This essentially describes the dependency of all the things. Once we describe the dependency, and if we need to compile this again, all we have to do is just call make. I'm going to make some quick changes here just so it will do it. If I do make, you can see that. Oh, okay. So I'm going to right. First command created from the main.cpp to the first object. Second command from food.cpp to the food.o. Last command putting them all together. So that's exactly what we just did. So makefile does this so that we don't have to type 3 commands at the end. We just type make and they create this for us. Right. This like from small project to huge projects, that's how it works. That LAPAC project I mentioned to you, if you look into it, it has a makefile. And it's gonna the compilation takes back then it takes about 10 minutes. So it's gonna do a lot of things. But this is also what happens behind the scene when we click here. So if we go back to the makefile, the downside of this is hard coded with G++. On my Mac, there's no G++. So that means if I want my code to run on the Mac, on the Windows, on the professor's Linux, I have to have 3 makefiles. And that's tedious. So the way to solve that, to make it machine independent, is to use a thing called a CMake. And what CMake does is that you just tell me roughly the file relationship. Don't worry about the compiler and all that. Once we describe that, we could the CMake would produce the makefile depending on what the system we're on. Okay, so I'm gonna go back here and create a simple or convert this into a simple CMake. So that is the CMake. And if I put this here and come back here and this is converting that makefile into a simple, like the simple list structure. What this does, it says we want to have executable. We have 2 CPP, that's it. Do whatever you want to do. As simple as that. And so save this. And once we have that, I'm gonna have a folder called build. It's simple as, okay, CMake ... means it's the upper level directory where the CMake list.txt is. Well, I need to install that too. Okay, so we run this. Before we run anything, there's nothing. And we run the CMake. All of a sudden, it created a makefile for us. And we do the makefile. It does not look exactly like what we have, but if you spend time, it's look roughly the same. It's doing the same thing. And once we have the makefile, we can just do make. And we have the foo.x. Same as before. So there's a few layer of things. One is you can do it manually with the compiler. On top of it, you can use the makefile. And if you need to run on different machines, you can use CMake to not have to write multiple copies of the makefile. If you go back to C line, you can see on the left, this is the CMake file. But this you don't have to dive too deep. But I just want you guys to know once you see the CMake, what that does, right? That is the magic happening behind the scene when we click the run button. That's it. For 342, I don't know, do you know the professor's plan on if you are working with larger projects, how do you compile?
I don't know. We didn't get there yet. We did do one project already, and it had 4 files.
Okay.
But we just, yeah, he just had to submit. And as far as compiling, it had like a .h, a .p something. Like 2 of the files couldn't be opened. Like I couldn't open it. It was like,
Okay.
it said like this isn't. I don't remember exactly what it said,
Okay.
but like 2 of them, they weren't like CPP files or
Okay.
anything like that.
Probably not even a text file.
Yeah, no, they weren't.
Okay.
They were like,
Okay. That's very likely the .o. So they compile it. It has some part that's gonna test something, test your code or do something with your code.
it was that. Yeah, so one .h, one
Lib, okay.
and then one .pdb.
Okay. Though the PBB sounds like something from Visual Studio. The lib is the same thing. On Windows, it's called lib. On Mac or Linux, it's called .o, the same thing. And in fact, what people do is normally they would combine a few .o into a .lib, and it's a library, right? Then you can use that. Yeah. Okay. Then for your project, probably you don't have that many files to justify having a makefile. But since you're already learning this, I would still suggest taking some time to learn how to write a simple makefile. And because this is going to be very useful. And the makefile is not just for C++, any language. You could use makefile for something. I think in my 342, the first homework is I took a song from a Pixar movie and put all the lyric into the makefile. And if you type make, it's gonna print all the lyric. And I changed the sequence and asked the student to fix them. So you understand the dependency between them. And one cool thing you could try to learn is try to do with, see if you can create your own makefile parser, right? Remember the makefile, to do this, we need this file, we run this command. And to get that file, we need to do this. It's very recursive, very like a tree structure. Then you could write your own parser to execute those commands and figure out, okay, I'm not ready to run this yet. I'm gonna call recurse myself into the next level and so on and so forth. So that could be a lot of fun. And that's just that. That's the compilation part, a bit behind the scenes stuff. There's one last thing I want to show you. Never mind. I took it out. So basically, what the thing is that see, let's see and see. For okay, so that's something that that's not that important. What I was trying to show you is with G++, you could also actually you could also create like a half, almost assembly code, almost machine code, and let me do this in the file. Add a And it's not really for this class, but this gives you a peek of what the machine sees. It's like we're speaking the language of the machine now. And in here, you could see that see if you can figure out where it's calling the full function. If I search for full, it's the full.cpp. And this is useful when if you want to have every bit of performance from code, then this gives you a view of what the machine sees, because the compiler could do a lot of things behind the scenes. So when it gets to the CPU, it's very different from what we write. But this tells you what the compiler will see. And then if this is something that you guys are interested in, you can learn how to write code like this. I did this 20, 30 years ago. It's super painful. It's like trying to write operating system with your knife. But for lower level machine, you could write this directly on that. And one cool thing we did is if you write a for loop with like linear algebra stuff, for loop is really bad for performance because it tries to predict what the next instruction is, but the for loop make it impossible to predict because you never know whether you're going to run out of the loop or not. So that hurts the performance. And the way to solve that is in here, you could take the loop, you could calculate how many times the loop is going to run. So take away the loop and just repeat that comment that many times. And once you see that in here, you see that it's predicting the next iteration because it knows exactly how many times it's going to run. And that increased the performance a lot. So this is not a 342 territory, or it is beyond that, but it's cool to see. All right, I think that's pretty much it. I have the stuff related to class, but this part is not that different from Java. And so I wouldn't spend too much time on this. You can still go back and read this part. The syntax is slightly different, but it's not that hard to see and understand this. Yeah, this, I don't know whether it's gonna get to that far in your class. The command that we need to pay attention is, for example, here in this class, it's called this. This is the class, this is the base class. We are allocating memory here. So where do you delete this? In the destructor, we need to remember to delete those memories. And there is a good, there's a big discussion about the destructor should always be virtual. But here, I'm not going to dive too much into that, but just be careful when you get to that. And the point is, if the destructor, if you have class A, then you have the class B derived from class A. And if the base class destructor is not virtual, then likely the memory is not going to be released. Because it's if you use, in this case, right, we have, this is a base class, this is a derived class. So if you do delete of the object using the base class pointer, so the pointer now point to the base class, but the pointer is actually pointing to a derived class object. And you do a delete that pointer, it will not call the destructor, it will not call the destructor of the derived class. And that means this never gets executed. So, but these days, if you write any code in the IDE, it would by default put it there. But it's important to understand why that's the case. Let me see. So that's pretty much it. We already talked about this. And I think it's good to stop here. Yeah, there's a few exercises. Feel free to try them. But since the semester already started, just focus on the class stuff. And that's it for today. Thank you.
Thank you,
Yeah,
Professor.
yeah.
I really learned a lot. I
Good,
feel
good.
really good. I'm so glad we came.
Okay, good, good. And share this with the other students.
Yes.
Yeah.
I definitely will. They should have come. They missed out.